There are two major types of lenses. We have the convex and then we have the concave. What's the difference? In a convex lens, parallel rays of light are brought to a focus. In that case, we call it principal focus. And then, if you look at the diagram you have here, convex lenses, they kind of like bulge outwards, while concave is thinner at the center. Now we'll get into the nuances later on as we progress. So distance between the principal focus and the lens, all right, is called the focal length. Remember what we said earlier, the principal focus is the point where all parallel rays, as you can see from the diagram here, all the parallel rays from infinity is brought to a focus at the PF, principal focus. But the distance between the PF and the lens, the midpoint of the lens, is the focal length. The focal length depends on how curved the lens is. So the more curved a lens is, the shorter the focal length. And then by extension, the more power the lens has. The power of a lens is measured in diopters. And then down to concave lenses. For a concave lens, parallel rays from infinity are made to diverge. They spread out, all right? So that's why we call them diverging lenses. When you look at questions, it's either the examiner refers to them as concave lenses or diverging lenses. And then for convex, they're usually referred to as convex or converging based on their properties. So the principal focus is now the point from which the rays appear to diverge from. Raise the rays backwards. It looks as if it comes from a particular point on the same side of the lens. That point is called the principal focus. So if we were to define that here, we would say it is the point at which it appears that the rays diverge from. And we represent that with dashed lines because they're virtual. So real and then virtual. We'll talk about that in a bit. So how do we represent these lenses? There are two major ways. We can represent concave lenses by just that first image or this when you're drawing ray diagrams. This or this. And then for concave, you can represent those ones with something like this. Whatever representation you want to use in an exam situation will still be right. Okay, now let's talk about real and virtual images. What's the difference? If an image is real, it means it is formed when light rays from an object converge and meet each other and can be projected onto a screen. So if you place a screen at the point where the image is formed, you get something. What are the properties of real images? Number one, real images are always inverted. Keep that in mind. Number two, real images can be projected onto pieces of paper or on screens. A good example of that is a projector. All right, it projects image onto a screen, and then you have some sort of arrangement inside it as well. Representation of real images, we use solid lines, two solid lines that cross in ray diagram. So real images, we use solid lines for the rays, solid lines for the images. And on the flip side, you have virtual images. What are those? Well, it's an image that is formed when light rays from an object do not meet, but appear to meet behind the lens and cannot be projected onto a screen. And what are the properties? Number one thing you need to know is that a virtual image is formed by the divergence of light away from a point. That's what we call the focal point of a concave lens. Keep that in mind. Two, virtual images are always upright. Typical example, let's walk back to a mirror now, your plain mirror, the mirror in your house. You're standing in front of the mirror, you're looking at yourself standing upright. So any mirror you're looking at or any lens you're looking at, and your image is, just standing upright. That's virtual. Remember that. Real images always inverted, virtual images always upright. How do we represent virtual images? We do that by using two dashed lines, or we could use one dashed line and one solid line that crosses. When we say line, we mean rays. And how do we draw this ray diagrams? How do we draw it? Number one, if an object is placed farther from the lens than the focal length, then a real image is formed. Anywhere you place your object, so far it's not less than the focal point, or we can say the focal length, whichever one you choose, you would always have a real inverted image. So from this point backwards, you place your objects here or here or here to F all the way backwards, you'd always get a real image. But once your object is lesser, or let's say your object is between the focal point and the lens, you'll definitely get a virtual image. And so how do we draw the rays? Number one, you start by drawing the first ray from the top of the object all the way through the center, unrefracted, with your ruler. Don't forget that. And then the second one, you draw it straight horizontal. And once it hits the midpoint of the lens, you refract it through the focal point. And the point where those two lines meet is where your image is formed. And sometimes to confirm the precision of your image, that's just like a cross check, you can just draw this. But you can see the third ray. It goes from the top of the object down through the focal point to the midpoint of the lens, and then horizontal. It meets at that junction. Then you draw your image all the way down. It's as simple as that. So image property is also a key factor here. How do we define this image? Number one, it is inverted, obviously. From the arrow, it's turned upside down. That is one. Is it real or virtual? Remember what we said. If we're drawing our rays with solid lines, then our image is real. That is one. And real images can always be cut on a screen. That's one. Two, this image you're looking at is magnified. It's quite bigger than the object. That is two. Three, is it upright or inverted? Yes, it is inverted. You can see it right there. So for the sake of emphasis, remember, convex lenses will always form a real image so far your object is placed at the focal length or at a greater length than that. But once your object is placed below the focal length, then you get a virtual image. Now, in what situations do we get a virtual image? We'll talk about that in a moment. We'll have a case where the object is placed at a position lesser than the focal length. So what happens here? You draw the first ray to hit the midpoint of the, let me use a pointer here. Yeah, you draw the first ray to hit the midpoint of the lens, and then it goes all the way straight down, unrefracted. You get the point. Then the second ray, horizontal, hits this point, and then it's refracted through the focal point. So this just goes straight down. And the most important part of this is you trace this backwards. So the point where these two virtual rays meet is where your virtual image is formed. And then you can see how we represented the virtual image. So to make things clearer now, let's pit these two guys against each other. You have the real image, that, and the virtual. You see the difference? Perfect. How should we define the properties of this particular one? Well, we can say the image is virtual. That's one. Two, we can say the image is magnified. Yeah, it's quite bigger than the object. And three, it is upright. It's not inverted. It's just standing straight like that. Okay. Here is a typical concave lens diagram. And how do we draw this? You draw a straight line that goes through the center, unrefracted. Okay, this is a bit way out of line, but this line, I'm going to adjust my drawing later. But one thing you should know, this line should go through this point. Okay, to go through this point all the way down, but you get the idea. That's the first ray. Second ray should be horizontal, hits this midpoint, and it's refracted upwards. It diverges. What next? You trace this divergent ray all the way down, dashed lines. Remember, we represent virtual rays with dashed lines. You trace it all the way down, and the point where these two guys meet is where your image is formed. And yes, this traced down should hit the focal point. So it will appear that this particular divergent ray came from the focal point. You get the idea. Qualifying this image, we can say this image is virtual, that is one. Two, it is upright. And three, it is smaller than the object. The images are always virtual, one. They're always upright, two. They're always diminished in all cases, regardless of where you place the object. But for convex, you see the difference. Convex, it is real up until the focal point, and it becomes virtual once the object is placed lesser than the focal length. Just a bonus here, the image is formed by the two mirrors. We can pit them against each other. For convex, we also call it converging. The image type always real, except if it's less than the focal length. So for the first one, this is magnified. This is magnified here, or diminished, depending on what your distance is. And in real fact, the closer your object is to the lens, the more magnified it becomes. Keep that in mind. That is for convex. And then when you move it at a distance lesser than the focal length, your image will be virtual, it will be upright, and magnified. For concave, also called diverging, the image type is always virtual. Image orientation, upright. Image size, diminished. Key point, convex lenses can produce both real and virtual images, but concave only produces virtual images. So that'll be all for this video. Remember to hit the like, share, and subscribe button if you learned something today. And I'll see you in the next one. Bye-bye.